Project 3.1, the CharlieClock. This is my Charlieplexed LED clock, a timekeeping system powered by an Arduino Nano that controls 132 LEDs using only 12 pins. Looks simple on the surface, actually demonstrates one of the most efficient lighting control methods in electronics, Charlieplexing. At the heart of this design is the Charlieplexing principle. Normally, each LED requires its own pin, but with Charlieplexing we take advantage of the fact that LEDs are directional, which means they only conduct in one direction. By connecting LEDs between pairs of pins and carefully controlling which pins are set to high, low, or input, we can independently control many LEDs from a small number of input-output lines. With n pins, we can theoretically control n times n-1 LEDs. So with 12 pins, this design can address up to 132 individual LEDs. That's exactly how this clock is wired. Each LED is wired between two of the Nano's pins, specifically using A0 through A1 for the first pairs, and D13 through D2 for the rest. This combination provides the 12 control lines needed for all 132 LEDs. Every LED is part of a logical grid, where each one lights up only when its unique pin pair is activated, as one output high and the other output low, while all others remain inputs. This circuit also incorporates a 32.768 kHz crystal oscillator. This component is commonly used in real-time clocks because it provides a precise, stable timing reference. Although this prototype does not yet measure exact time, the oscillator acts as a theoretical time base for the circuit, showing how the design could easily integrate an accurate clock model in future iterations. The physical layout was modeled in Fusion 360. The goal is to create a clear symmetric LED arrangement similar to traditional analog face, where each LED corresponds to second or minute mark, allowing the clock to visually represent time as a circular progression of the lights. I used 4 buttons to simulate user input and adjust clock functions. These are connected to analog pins A2 through A5. Each button serves a distinct purpose: one to increment hours, one for minutes, one to start or stop the clock alarm, and one to snooze the alarm. To make the button input reliable, we used hardware debouncing. Without the debouncing, quick mechanical vibrations in the switch could register as multiple presses, causing inconsistent input. The debounce filters these signals so that each press counts only once. This project blends coding, circuit theory, and 3D design into one cohesive system, showing that with a few components and some creative problem solving, it's possible to control over 100 LEDs with just a dozen pins.